Hello everybody, my name is Sualp Ozel and I'm the product manager for Autodesk Simulation Mechanical. In this presentation, I will introduce the new features included in Autodesk Simulation Mechanical 2014, and I will also point out the many benefits you will experience by using this exciting new release. Over the past year, we've talked with a number of customers to get a basic understanding of their usage and their needs from the software, and that feedback helped us identify 5 key focus areas for this release: parametric optimization, simulation CFD interoperability, new loads and constraints, basic usability improvements, and new and faster solvers. Now, let's take a look at some of the highlights of how Autodesk Simulation Mechanical stacks up on these projects. In the subsequent videos, you will be able to focus on each one of these projects and many more benefits that the 2014 delivers. Parametric design studies is a new functionality we've implemented for linear static stress in the 2014 release for models built using Inventor. This feature allows you to read in and change parameters for a CAD geometry without altering the original Inventor model. The tool also has a built-in comparison table to easily locate the best design that fit your criteria around weight, stress, and deformation reduction. Once you find the best design that fits your criteria, you can then promote your final design back to Inventor as well. This feature will allow you to fully leverage your investment in simulation as well as the rest of your Autodesk tools. Now, let's take a quick look at the workflow. All right, we start the parametric design studies by opening an Inventor file. And you will notice that now you can look at the Inventor models in preview mode. And we'll set our analysis type as static stress. Here we're dealing with a single part, but of course parametric design studies support assemblies as well. The first thing that we do for setting up an analysis is to mesh the geometry. Then we'll assign some loads and boundary conditions. Once all the loads and boundary conditions are analyzed, in the ribbon, we have this new button called Parametric Design Study, which automatically brings in all the parameters defined in Inventor. In this case, I'm picking 2 parameters at the bottom, the large radius and the small radius of this object. And using the built-in functionality, I can assign different ranges for those features. So let's say I want my radius to range from 25 to 37. I can do that, and I can put how many different options within that range I want. In this case, I wanted 3 options in the first parameter and 4 in the second. 3 times 4, that gives me 12 options to run. And at the bottom, when I hit Run Simulation, all those options will start running, one after another. Of course, we go through the same meshing process, the model updating process, and the run process for all 12. This could take a little bit of time. So to save time, let's skip to the results. Once the analysis is complete, you have a table of all these 12 results. You can sort them using the maximum omni-C stress, the weight, and the deformation. And we have a little thumbnail of each different design based on the parameter combination that makes up this specific design. We have a little filter built on top, so you can type in a certain range. So for example, if you want to look at everything that's less than 40 psi in this case, you can do that simply by typing 40 and applying that filter. And if you pick a more specific filter, in this case we picked 20 for our maximum stress, that leaves me with a single option. You can of course disable your filters and look at the big picture again and export your results as a comma-separated file, which you can then open in Excel or any other file that can open a comma-separated value and look at your results in a different data editing tool. You can create all kinds of custom graphs in your post-processing using secondary tools like Excel in this case. And another thing you can do is you can launch a specific file directly from within that table. If you just double-click on the thumbnail, it will bring you to that specific model. And once you're in the results environment for that model, you can do all kinds of post-processing, such as looking at your deformation, stresses, and strains for that specific model. So in this video, we've covered the parametric design studies, where we've taken an inventor file, sent it to Simulation Mechanical. After meshing and setting up loads and boundary conditions, we've set up 2 parameters to alter and did a design study on 12 different options and picked the best one that fits our criteria. So in this video, we'll talk about the Simulation CFD to Simulation Mechanical interoperability project that we've implemented to the 2014 products. Many of our customers use Simulation Mechanical alongside our other simulation products, and they want to use them together to solve more complicated problems. In the 2014 release, we're opening up new workflows that allow SimCFD to be used with Simulation Mechanical. Thermal stress is a common concern in electronics packaging, industrial machinery, and many other areas. In the 2014 version, CFD thermal results can be mapped to Simulation Mechanical as thermal loading to calculate thermal stresses. This project was implemented to support both steady-state and transient thermal analyses, and it allows for additional flexibility because simulation CFD meshes can be totally different than a simulation mechanical mesh, and we have the capability to map those results from a simulation CFD mesh to simulation mechanical. As a result of this project, customers who have multiple Autodesk simulation products can use them together to solve more complex problems this year than they have in the past. So now let's go into the software and see how this workflow will be implemented. We start our simulations by sending a mechanical model from Fusion to CFD and running a CFD analysis. When that analysis is complete, we send our model to Simulation Mechanical and generate our mesh and apply our material properties. The one thing to pay attention is to make sure that the material that we pick has a thermal coefficient of expansion. Another thing is the stress-free reference temperature. This will be the temperature to look at between the applied temperature and the stress-free temperature. Once all that information is added to a model, we can continue to set up the geometry by adding the appropriate loads and boundary conditions. In this case, we're dealing with a half symmetry model, so I'll apply the symmetry conditions to the cut planes. And once all the symmetry conditions are applied, I can then go into the analysis parameters, and in the thermal tab, turn on the thermal loading and add a custom description to that specific load case. Then we go to the thermal tab, and you will notice a completely different menu here. And one option in this new menu is to map results from a previously run CFD analysis. Then all I have to do is browse to the appropriate CFD file and pick the appropriate design scenario within that CFD file. This CFD file I'm mapping to had 2 different design scenarios, and if I name them with the proper descriptions, I can easily pick the appropriate design scenario from the CFD. Now I'm running this analysis, and keep in mind, in this analysis I had only boundary conditions and no additional loads other than the thermal loads I've mapped from SimCFD. So I'm seeing a deformation result by default. I can of course change my result type to show the applied load, which in this case is the thermal loading, and this will match the temperature profile that we were seeing in our SimCFD analysis. To summarize, in this video we've taken a geometry, pushed it into Simulation CFD, and ran our CFD analyses. Then we pushed that same geometry into Simulation Mechanical, meshed it with a complete different mesh style and size that is appropriate for a mechanical simulation, mapped our thermal results from CFD to mechanical, and ended up with different stresses and deformations that is appropriate for the structural analysis. In this slide, I will cover drop test simulation, which is a new functionality we've implemented to our 2014 release. Majority of our customers are in industrial machinery, and drop test simulations are a common requirement. The image on the left is showing a physical drop test for a missile packaging design. Such physical tests are often very time-consuming and expensive, which makes them a perfect candidate for digital simulation. Historically, the setup of these simulations, which I'm showing over here, were very time-consuming and involved many steps. In the 2014 version, we've taken this problem on and reduced it down to 3 steps. With this new improvement, an average user will be able to set up and start a drop test simulation within seconds. So now let's take a quick look at how this workflow takes place on the interface. Here we have our model imported into Simulation Mechanical, and it has already been meshed. Once again, in the ribbon, we have a new icon called Drop Test, and when we access it, we get a new dialog populated. You can define the drop height and the drop direction, and it will automatically create an impact plane for you, and you will be able to visualize it in the interface directly. Here, it's shown right here. You can set up this drop with a stationary or a moving condition. And once you go to the 3rd step, it automatically calculates 3 different time zones, one for the free fall, one for the impact, and one for the rebound. Of course, all these fields are editable if you just turn off the automatic field. And once you're done with the 3rd step of the dialog, you're already in the analysis. As the analysis is taking place, you can immediately take a look at your results. And within seconds, you will reach the impact zone, which is when the exciting stuff is happening. So by default, we only give you a handful of results for the free fall section. And we try to give you as many results as you can see here with all these points for the impact section. We've taken an historical simulation setup that would require you to define the impact height manually, the impact plane manually, the gravity load manually, as well as its load curve, and the event time zones manually, and reduced it down to a 3-step interface, which will allow you to set up these simulations and run them with ease. In the next couple slides, I will talk a little bit about the new improvements in terms of loads and boundary conditions, as well as our solver technology. The first one that we've added in terms of new constraints is the cyclic symmetry. This improvement is implemented for 3D CAD models, and whenever a user is analyzing a rotating machinery, such as a blower or a fan, they can analyze only a slice of the model instead of the full model, and still get results on rotating machinery with higher accuracy and within a fraction of the time. Let's move on to our solver-related improvements. In the 2014 version, we've implemented 2 new solvers. The first one is a new AMG solver that we've implemented, and it makes use of NVIDIA GPUs if you have them available, and it's good for linear static stress and MES analyses. For certain machine configurations, this will result in significant solution time improvements on these 2 types of analyses. This new solver is only available for Windows and is not supported for Linux at the moment. Another solver we've added to the system is the Subspace AMG solver, and this one is good for modal analyses. And if you're solving a really complex model with a lot of elements, and if you're only looking for a small set of mold shapes, this will give you a significant improvement. So I have 2 models here that I've put on this slide to show that for these specific models, for example, when I only solve the first mold shape, I get 50 to 60 times faster results. In this slide and the next one, I'll talk a little bit about some of the work we've done around meshing and CAD import for Autodesk Simulation Mechanical 2014. Whenever you're dealing with assemblies that have both solid and surface geometries and trying to import them to Simulation Mechanical, you often end up changing the mesh type for surface geometries. In the 2014 release, we've added the capability to recognize those surface objects and change the mesh type automatically to plate and shell so that our users, upon import, can simply click the Generate 3D Mesh button and get a successful mesh. This improvement has a secondary benefit such that when they are trying to do parametric design studies, those surface objects, such as the ones that we've shown here in transparency, will come into Simulation Mechanical every time after a geometry update, and the parametric design studies will run successfully and give them the new geometry and the new results based on the parameters that the user sets. We've done a couple other improvements to meshing, and the second one is around part imprinting. So if you're dealing with a surface-only geometry and importing your full assembly as a single part, we've implemented a new feature called imprinting within parts. And this is especially beneficial when you have two adjacent surfaces coming together and you want good mesh matching to get accurate results. And the third one around meshing is has more to do with databases around meshing. In the 2014 release, we've implemented a capability to delete mesh, which will allow you to select a certain part or a group of parts and delete the mesh associated with that and clean your database to start a simulation from scratch. This was a common enhancement request from our user base and will be beneficial to those advanced users who want more control over their mesh structure. Now let's take a look at some of the associativity improvements we've done on this release around meshing. Oftentimes when we set up an analysis and run it, we want to refine our mesh several times to make sure that our results are accurate as the mesh gets finer and finer. So in the 2014 release, we have implemented an associativity for some of the nodal loads and boundary conditions. This was another common request from our user base. So whenever you're dealing with nodal loads and boundary conditions assigned to set coordinates, such as the ones in the center points of joints, bolts, and remote loads and constraints, those will be kept in our database as associative items. And whenever you remesh your geometry, so in this case I go from a coarse mesh to a fine mesh, we will automatically assign those loads and boundary conditions to the center points of bolts, joints, as well as some remote coordinate that you've picked in space. And this will allow you to try what-if studies and mesh convergence studies with higher accuracy. Now let's take a quick look at how this works in the software. Okay, here I have an inventor assembly, and it is made up of multiple solid objects and surface objects. Those surface objects come into Simulation Mechanical 2014, and the mesh type is automatically set as a part mesh object, and it is set to plate shell, as you can see, which allows me to just simply click the Generate 3D Mesh button, and it will automatically assign brick elements to the solid objects and plate elements to the surface object. When I define its thickness, I'm essentially ready to set up the rest of my analysis. So I add some loads and boundary conditions to finish the setup, and then I can run my analysis. But I also want to highlight this new functionality of nodal associativity, so I'll add a joint. I select the surfaces at that hole and create a joint. And you will notice that you can set your part, surface, and layer information for joints in this release as well. So I select the material and select the central node to assign a nodal constraint. Now, let's say if I want to define a finer mesh, I change my mesh size to a finer percentage and remesh the geometry. And you will notice that the software will automatically not only keep your surface loads and boundary conditions, but it will also keep your nodal boundary condition that's at that center point. It also keeps your element type, element definition, and material information for solid objects and surface objects. To summarize, in these two slides, we've talked about some of the new meshing improvements we've done to the 2014 release. and we covered some of our nodal associativity. In the next couple slides, I will talk a little bit about some of the additional usability improvements we've introduced in the 2014 release for Autodesk Simulation Mechanical. I will highlight some items in our FEA editor, which is our preprocessor. I will talk a little bit about the results interface and material library manager. And then I will touch on some of the improvements to the report generator. So this first slide, we're going to be talking about our FEA editor improvements. And the first one is pretty straightforward. In the application menu, you can immediately take a look at recently accessed simulation files. And by default, they are listed as line items, but of course you can change your visualization from list items to thumbnails. And in this release, we do show you the full thumbnail for the object you are looking at. This makes it really easy to re-access some of the files that you've opened in the past. Another one is the preview of Inventor files in the File Open dialog. So when you go to the File Open dialog and change your CAD Open type to Inventor Parts or Assemblies, you will see a little preview of the Inventor geometry prior to opening it. This will once again allow you to access that geometry much easier and more efficiently without making the mistake of opening the wrong file. The next one is the use of strike-through fonts. So over here, we have the list of parts that you have imported from your CAD geometry. And if you suppress a certain part, we now use a strike-through font for that part, which lets you easily identify that part in the list of your objects. And then the final one is the use of load cases and the ability to apply custom descriptions to those load cases in static stress. If you are in static stress and if you access analysis parameters, you can define multiple load cases. A common use case could be the first load case is for your thermal loading, and in the second one you want to combine your thermal loading and internal pressures, for example, and in the third one you want to include the effects of gravity. As your number of load cases increase, it might be difficult to manage all those load cases. So let's say you have 20 or 50 different load cases. Adding a quick description about what that load case is, which is also shown in the results environment as a default annotation, will help you understand which result you are looking at and what load case it is of that result. All right, let's move on to our material library manager and material applicator. So we have made some improvements to this interface as well. And I think the biggest one and the most important one is the ability to use different custom unit systems whenever you're actually inputting a material to the library. So let's say you have a material, but you have your modulus of elasticity in one unit system and your density in another, and your thermal coefficient of expansion, for example, in another unit system. In the past, you would have to convert all those material properties into a common unit system that is allowed by the material library manager. But in this release, we've included the unit systems dialog directly into the material applicator, and material library manager, which when you start typing your material information into these fields, you type one information, hit save, and you can then change your unit system to the next one and move on to the next field and enter that. This will save you a lot of time and avoid confusion in terms of constantly doing manual conversions for different units. The next improvement is about the visualization of the material information that you've entered. So if you're dealing with temperature-dependent materials, the material library manager allows you to enter all that information in a table format. And with the view plot, you can visualize how the modulus of elasticity changes over temperature, for example. In the previous releases, all the material information that you've entered, so not just modulus of elasticity, but for example, Poisson's ratio, thermal coefficient of expansion, all of that was graphed in a single graph, which made that graph look very busy. In this release, we've implemented the different checkboxes here, so you can pick and choose which ones you want to graph in this environment. And of course, you can take that graph and take the information on that graph and put it into your reports to explain how your material properties change as well later on. And the last improvement is around how you enter material properties. In static stress, when you're dealing with isotropic materials, you only really need two pieces of information. You need modulus of elasticity and Poisson's ratio. Of course, if you have Poisson's ratio and shear modulus, you can back calculate modulus of elasticity. Or if you have shear modulus and modulus of elasticity, you can calculate shear modulus. So only two of the three are needed. But if in the previous releases, we allowed you to enter all three pieces of information, which sometimes if you made a math error, for example, there could be redundancy in the material information and you could end up with errors or warning messages. In the 2014 release, we've eliminated the shear modulus from the list of items you can enter, and it's always automatically calculated based on Poisson's ratio and modulus of elasticity. All right, let's move into the results environment. In the results environment, we've made three key improvements. So the first one is the ability to inquire minimum and maximum results on a per part basis. So if you look at the ribbon up here, the second item on the ribbon will be results by part. This is a new icon, and if you have an assembly with multiple parts, you can just inquire the minimum and the maximum result in a table format that you can then of course export as a text object and dump it into your report to showcase your results in a more efficient manner. And this will be very useful for assemblies, for people who are analyzing assemblies with a large number of parts, because in the past you would have to literally isolate a part and look at the minimum and maximum result of that object one by one. And if you have, for example, 100 parts, that could take a long time. But in this release, with the single button click, you will get a list of all the minimum and maximum results on all the parts in a nice format. The next improvement that I will highlight is for the report environment. So here I have an excerpt from our report environment, and this is the material information. For all the different parts that you use in all the different materials, we will automatically showcase the yield and ultimate strength of the material properties that you've used. So if you're dealing with material information that you're bringing in from your CAD geometry, for example, or if you have selected a material from our library, or if you created a custom material in the Material Library Manager, your yield and ultimate strength will always be displayed here. And then you can understand where you stand against these numbers for your von Mises stresses, for example. And the last one, last bullet point that I highlighted here, it's referring to some new tables that we've added to the report environment. So this is a large list, so I'll just point them out in general. We've added three groups of tables to three groups of analyses. So the first one is for static stress. In the static stress reports, we've added a new table to explain the centrifugal loading that you've implemented. The next one is for mechanical event simulation, MES. In addition to the centrifugal loading, we've implemented another table for the event information, another table for the load curve information, another table for the gravity information, and of course the centrifugal one. So there are 4 new tables in the MES. And the final one is around our modal analyses. For the modal analyses, we didn't necessarily include a table, but we've added a new file to the bottom of the report where your summary and log files live. Those are the processor information. We've added a new one called mass participation factor. So by simply clicking that file, you will see the mass participation factor for your X, Y, Z directions in both translation and rotation in a clean table that you can, of course, include in your reports and export to your standard Word documents or PDFs or HTML documents. So these are the highlights for all the improvements around usability for our preprocessors, our post-processors, and our report environment. We hope that you will benefit from these improvements, and we can't wait to hear back some of your feedback on some of these improvements. Thank you for watching.